So now let's move on to boundary conditions. Again, this should be a refresher for most of you. So we'll start with what are called as tangential boundary conditions. Okay. So in tangential boundary conditions, I want to get a relation between the tangential electric fields or tangential magnetic fields, as the case may be, right. So let's take a medium over here. So let's call this medium 1 and medium 2. When I say medium 1 and medium 2, so medium, what is different over here? What differentiates one medium from another medium? Epsilon, mu and sigma, right. So that's, we can say epsilon 1, mu 1 and sigma 1, and similarly for medium 2, okay. And it's a surface, so a surface is going to be characterized by some normal vector over here, okay. So let's say that this continues over here, and I want to get a relation between the tangential fields. So we have all done this in undergraduate, right. What do? You take a small little wire frame that straddles the boundary. So it's half above the boundary, half below the boundary. Okay, let's take something like this. Let's call this delta y and let's call this delta L. Okay. So if I want to, let's say, get a relation between the electric fields above and below the boundary, that's my objective. So what do you suggest I do? So I want the electric field along this curve, okay, and what I am going to do is I am going to make delta y tend to 0. That's what will give me the relation just above and just below, okay. So I want to go along the boundary. So which theorem? Stokes theorem is what is going to help us, right. Stokes theorem needs a curl, and I see Maxwell's equation over here sitting with a curl. It's like ready made for me. So what do I need to do to this equation to get it into Stokes form? I need to integrate, that's right. But what kind of integration? The line integral. But I don't see a line integral. If I am going to get a line, okay, a line integral is there on one side of Stokes equation. What is the other side? Surface integral, right. So if I take this surface over here, right, it's an open surface bounded by this boundary, right. So I can say, okay, I am going to integrate over this surface, and what way is the surface normal pointing? The surface normal is coming out of the board, okay. So I can do this del cross E dot ds, right. And this is where Stokes theorem helps us, and this is what I get, E dot dl, okay. Now when I look at the right hand side, I can substitute del cross E from this equation over here, right. So there is no special way to simplify it, it will remain as it is, okay. So this will become minus j omega b minus m dot ds, okay. So far all I did is I took my Maxwell's equation over here and integrated over this shaded surface over here. Is that fine? Alright. And Stokes theorem simplifies this over here as E dot dl over the contour. So when I start from, let me start from this point over here and work my way all the way back over here. So we'll assume that these delta L and delta Y quantities are small, such that the electric field is constant, piecewise constant along these edges, alright. So I have E1 over here and I have E2 on this side, yeah. N cap is just the normal vector for this surface that defines the boundary, okay. Because whenever I define an interface, how do I define the interface? So I give the surface normal, the interface is defined. Alright, so when I start from this point over here, E dot dl is going to give me what? So I will get E2, but not just E2, I will get the tangential part of E2, right. So E2 tangential multiplied by delta L, okay. Then I finished this part, then I move to the next segment. What do I get? Plus E2 tangential. So let's call this, so instead of calling it delta t, let's call this E2 along say x direction, right. and this E2 is going to be along y direction, and how much length? Delta y by 2. Similarly, if I go further, I am going to get E1 y delta y by 2. Next term minus E1 x delta L, then minus E1 y delta y by 2 minus E2 y delta y by 2. So, what I have done? I have calculated this line integral piece by piece. Okay. So, I am going to take the limit, this limit delta y tending to 0. Okay. So all the delta y terms over here, they are going to become, they are going to tend to 0. Okay. Another assumption we are making is that these fields are physical quantities, they are not going to blow up to infinity. So, when a finite term is multiplied by a vanishingly small term, I can get rid of it, right. So, what I will be left with is E2 x minus E1 x multiplied by delta L, right. And on the right hand side, what do I have left now, right. So, I can say that, so this for example, I can write it as minus j omega b plus m multiplied by delta y delta L, that is the surface, and we are assuming that we are talking about the component of b and m, that is along the ds vector. Okay. So, let me, so is that's clear, right, because I have to take the dot product between this vector and this vector over here. So, whatever survives along this, that is coming out of the plane of this page, is surviving in this term. Okay. That is the only term that is retained. Okay. So, if you want, you can put a hat over here. Okay. What can I do about these terms, or what can I say about these terms? Which terms will survive, which terms may not survive? What about the first term? Magnetic field multiplied by dy dl or delta y delta L. Would it be 0 or non-zero as I take the limit delta y tends to 0? It is a magnetic field, it is a physical quantity, and we do not expect a physical quantity to blow up. There is no there is nothing special happening at this, just a boundary between two interfaces. So, what can a reasonable assumption to make is that as I shrink this delta y to 0, I have a finite quantity multiplied by a vanishingly small quantity, right. So, this guy is going to actually tend to 0. What about this current over here? This is a magnetic current. Forget for a moment whether it is physical or not physical, it is some quantity over here. Can it be finite or can it be infinite? So, if it is finite, that means this contribution will tend to 0, right. So, that is one case, easy to handle. The other case is, supposing it is infinite, how can it be infinite? So, infinitely conductive material, right. So, like if you take a perfect electric conductor and I ask you where is the current on the conductor, in how much thickness is it? What would you say? No, it is a perfect conductor, sigma is infinity. Then what will you say, how much thickness is the current flowing in? 0 almost, right. It's a pure surface current. So, if it's a pure surface current, only then, in the sense that at the interface itself, its value is infinite, right. But this m into delta y, that will be a finite quantity. Okay. So, that is what is called a pure surface current. Okay. So, if I keep this over here, the only term that has a possibility of surviving is minus m hat delta y delta L, and this term I will call as ms. Okay. So, to sort of state that again, this m hat, if it is a pure surface current, is going to be very, very large, but this very large quantity multiplied by a vanishingly small quantity is what is going to give me a finite surface current. We are not used to thinking about it in such threadbare means, but that is how we arrive at this equation, right. So when I compare both the left hand side and the right hand side, what I get is, so this and this I am going to compare. Okay. So this E2x, this is nothing but the tangential part of electric field below the medium, and E1x is the tangential part of the electric field above the medium. Okay. There is a delta L here and there is a delta L here. These will cancel off. So when I combine these two equations, I must combine them keeping the vectors in mind, right. So when I combine these two equations, you will see this is the equation that I get. Okay. So you see this, that is why I defined this n over here. So let us take an electric field over here, let us say E2 is pointing like this, right. So E2 cross n, E2 cross n, if E2 is in the plane, n is in the plane, where is n cross E2 pointing? Outside the plane. Will it be tangential to the boundary? N cross any vector will be perpendicular to n, and n is perpendicular to the boundary. So n cross E will always be along the boundary, right. So this is one very clever way of using vectors to give us the tangential field immediately. The high school way of writing it is like this, E2 bracket x or E2 bracket tangential. That is how you have seen, E tan 1 is equal to E tan 2, but we can write it in a more sophisticated way now using the language of vectors. So just to summarize, n cross E is going to be perpendicular to n, and what is perpendicular to n? The interface. So it is the so this what is written over here, this is exactly the tangential fields. Okay. And what is left on the right hand side is simply this thing. So I will call this the pure surface current. Right. So I can repeat the same exercise for the second Maxwell's equation, right. Again there what do I have? I will have del cross H is equal to, so j omega d plus j, right. I can mimic the same proof line by line. The only thing that will survive, so this guy is d is a physical quantity, a displacement field. When I stick it into a surface integral, I can say it is, the contribution will vanish. I will only be left with a j, and this time j is carrying a positive sign. In this equation, j was carrying a m was carrying a negative sign. So you can see that this relation is what I will get for tangential H fields. So this is tangential E, and this is tangential H fields, right. So what is this again over here? This is also a pure surface current. Pure surface currents means it lives in the surface in a vanishingly small thickness. Only then can it contribute. So if I take a non-conducting medium, let us say you take glass, wall, floor, whatever, right, you don't, there are no, it's not, they are not perfect conductors. So in that case, what is the most commonly used way of expressing boundary condition? Tangential fields are the same, right, that is because these guys Js and Ms are 0. So you get E tan 1 is equal to E tan 2, and we write that in the language of vectors using n cross. Okay. Have you seen this derivation before? Okay, very good. So this is as far as tangential boundary conditions go. The other, so you notice that we used the first two equations of Maxwell, right. So you can ask, okay, what happens when I use the remaining two equations, right. So that takes us to normal boundary conditions, and I will use, so I think I made a mistake over here, this should just be plus A, right. Normal boundary conditions over here. So again I have an interface over here, this is medium 1 and medium 2, okay. What is the way of finding a boundary condition over here, if anyone remembers? Take a cylinder, right. So if I take a cylinder like this, okay, so this is medium 1 and 2. The hint for whether to take a open surface or a closed surface, how would you get that hint? That hint comes from looking at the integral form of Maxwell's equations, right. Over here, when I did this equation over here in integral form, I was taking curl Curl I know by Stokes theorem is going to convert to a line integral, so I needed a open surface. When I come to this equation, I have a divergence term, and I know that the theorem that applies to divergence has a volume integral. So I think of a volume pill over here. You can try applying this theorem on a wire frame like the previous example. You will find that you don't go anywhere. Okay. So if I take this over here, then as we already mentioned, the theorem that we will use is divergence theorem, right. So if I take a volume integral on both sides, so del dot d dv, and this is going to give me the flux of d, right, flux over the closed surface, right, d dot ds. So I have a delta y over here and a delta s is the area over here, fine. So exactly similar to what we did in the previous example, I will calculate this integral on by both ways. So in this case, maybe we don't need to go through the entire derivation. So what we can just sort of intuitively see, del dot ds, how many surfaces should we break this up into to evaluate it? So this, for example, this is one surface, the top cap, then the bottom cap 2, right, and then there is going to be some contribution from the curved surface. And I know that contribution from the curved surface, what will happen to it? It's going to go to 0 because I am going to take the limit that delta y is going to 0. I want to squeeze this pill as much as possible, so I get a relation between the fields here just above and just below. I don't want the relation between field here and field here, that's of no use, it's not a boundary condition. I want to shrink these guys down to as close to the boundary. So what will survive will be whatever is contributing from these caps over here. Now what is the surface normal for the cap over here is like this, right? That is what is will contribute to the outward flux. What is normal to the surface is flux. So as I shrink this delta y down to 0, the normals to these caps will be along the normal to the surface itself, right, to the interface. In this case it will be plus n, in this case it will be minus n hat, right. So when I do this accounting over the 3 volumes over here, I will be left with, for example, let us just write it over here, d1 normal component multiplied by delta s and minus d2 normal component delta s, okay, and plus one term which is, let us say, 2 pi r delta y, right, that is the curved surface area, and this term is going to go to 0, right. Then the remaining tricky part is to look at the right hand side over here. So the right hand side is going to be rho e dv, right. So how much charge is enclosed in this volume integrated over dv, and this dv is going to be rho e dv, I can write simply as delta s and 2 pi r delta y, right. That is the volume of this cylindrical box, right. Now what can you say about this, whether will this be 0 or not? There is no? Yeah, there is no integral over here, we got rid of it, let's, yeah. So will this be 0 or non-zero? Under what condition will it be 0 or non-zero? Exactly. So just like in the case of the current discussion, if I had a volume charge distribution, a charge that is distributed through the volume, then what will happen is, it's a finite charge residing in a volume that is shrinking to 0. So its contribution will be negligible. On the other hand, if I have a pure surface charge, that can again happen for like perfect conductors. You take a perfect metallic conductor, put charge on it. Where does the charge live? Purely on the surface, right? So the only possible way for this term to survive is if the charge is a pure surface charge. So this is a pure surface charge. Okay, and n dot d2 and n dot d1, this captures the normal component of d1 and d2. Okay, that is the only part that will survive the dot product with n hat. And I can repeat the same logic with the second divergence relation, and I will get, so this is also a pure magnetic charge. Okay. Is that fine? So, keep these techniques in mind. You will have to apply them depending on the problem at hand, and these, like you can see, we are just using the tools of vector calculus to simplify a surface integral into a line integral or a volume integral into a surface integral. That is the basic idea over here. Okay. So, let us look at what is the power in a field. So, again this should be familiar to all of you. You have what is called the instantaneous Poynting vector. Right? The definition of instantaneous Poynting vector is simplest when I look at real valued physical quantities. Okay. So, in terms of that, it is simply the cross product of E and H. Okay. It does not get simpler than that. This expression gets a little bit more complicated when I introduce my phasors. Right. So, I want to now find out, I want to express this Poynting vector in a phasor notation, because I am going to do all my calculations in phasor. I should have an expression for power in terms of the phasors. Right. So, we have already done this, the real valued quantity is expressed in terms of the real part of the phasor. Right. So, if I ask you to simplify this, how would you write down the real part of a complex number? Cos is one way, another way would be, supposing I give you a complex number z and I ask you give me real part of z, half of z plus z star, z conjugate, right. So, I can also write this as half of, so e to the j omega t plus e star e to the minus j omega t. Okay. So, that is as far as the electric field goes. Similarly, I can do the same thing for H. I will write it as half of H e to the j omega t plus H star e to the minus j omega t. Okay. So, what do I next do is I am going to take this expression and this expression and put it into the expression for Poynting vector. Okay, and we will see what we get. So, when I take the cross product between these two quantities, how many j omega t terms will you observe? So, for example, when this guy combines with this guy, what will I get? I will get e to the 2 j omega t. When this guy combines with this guy, what will I get? I will get e to the minus 2 j omega t. Similarly, when this guy combines with this guy, what will I get? No, DC, I am going to get 0. And similarly, when this guy combines with this guy, what do I get? Frequency terms are, the phasor terms are 0, right. So, even without doing all the opening up all these expressions, I know that these are the frequency terms that I will get. I will get a 0, I will get a 2 j omega t. It is not possible for me to get a e to the j omega t, right. You can just intuitively see it immediately. So, when you simplify this further, let us write down S, what expression you get is first term is this, which is at 0, and the second term that you get is okay. So, all the boundaries of brackets are fine. This is what I get. Okay. So, you see that the power seems to have two components, one is at DC and one is at 2 j omega t. So, if I take the average, a phasor that is oscillating at twice the frequency has how much average? 0, right. You integrate cos 2 omega t over one period, the wave has undergone two fluctuations, its average is going to be 0. So, that is why the average power, only the DC term survives, right. So now you have a very, and usually we are interested in average power. Okay. So average power is now given in terms of the phasors, the real part of E cross H star. Okay. So this is conjugate H and take half of it, right. So you can see that the power, this E cross H term over here, E cross H star can be real, can be imaginary, right. I mean, it will have both parts, the complex number. So the real part is going to give me the power, and what about the imaginary part? What do we call it? People from circuits background? Reactive power. Okay. So this concept of real power and reactive power will be very interesting when we look at the radiation from an antenna. In the near field of an antenna, most of the energy is reactive. As I go into the far field, we will find that it becomes more and more real. Okay. So it's not just for theoretical fun, it's actually happening in nature, these things. Okay.